So this is the laboratory activity 6. The important of PS and P is the library used for numerical and mathematical operations, especially for handling arrays and mathematical functions. The matplotlib, the pyplot, is used for plotting and visualizing data like line graphs, stem plots, and titles. So the next line, the F signal is equal 5 and T equal N dot linspace 0, 1, 1000 and the X equal NP sine 2 times NP dot pi times F signal times T. This sets the signal frequency to 5 Hz. This line creates a time array from 0 to 1 second with 1000 equally spaced points, a smooth time base for continuous signal plotting. So the XNP, it generates a sine wave of 5 Hz using this formula 2 times NP dot pi times F signal times T. So this line, the pi plot TX label continuous signal, it draws the continuous sine wave. It also has the title or the label, and to make the plot clear and readable. The PLT fig text has these axis coordinates and my name, the font size, and the color. Um, it displays or it writes my name on the figure at a specific position. PLT show is to display the figure on the screen. So the next is the sampling parameters fs high and the fs low. For fs high, high sampling rate, 50 samples per second above Nyquist rate, no aliasing, and the fs low, 6, the low sampling rate, 6 samples per second below Nyquist rate, will cause aliasing. So creating sampled signals, this line, it creates this NP range 0, 1, 1 over fs. It creates time point space by 1 over fs seconds, simulating the sampling times. The x high and p sine and xl low, this two below, it is the corresponding sampled values of the original 5 Hz sine wave. So the PLT figure, it is the plotting proper sampling. It creates a new figure with a wider size. So the PLT plot, it plots the continuous signal and its discrete samples since fs is equal to 50 hertz. This part is much higher than 2 times 5 hertz is equal to 10 hertz. Sampling satisfies the Nyquist criterion, so there is no aliasing. So the PLT212, this line, the samples taken at 6 hertz, which is less than twice the signal frequency. The discrete samples now misrepresent the actual signal, appearing as a slower or distorted wave. This is aliasing, which is this. So the VLT fig text, this line, it adds my name to color green, which is it displays the final figure with two subplots, proper versus undersampling. So let's see the output. Hmm. There, as you can see here, this is the continuous time signal 5 Hz sine wave with the labels. and this is due to proper sampling in the undersampling waveforms. This has no aliasing, and this has aliasing since it is 6 hertz. So